Hello everyone. Every time we start a new project, we are posed with the question, what about the data store? Now we might go about answering this question in quite a few different ways. There is a shiny new database in town that I want to explore. Or the data intended for my application is well structured, has good definition, so I want to use an SQL store over a NoSQL one. Now, all of these opinions and more are probably valid based on what our intention is to build the application or what the application's requirements are. I'm here to propose an alternate way of evaluating database choices, the asset-based way. Why? Because database choices go a long way in ensuring the robustness of your application. Hello, everyone. I'm Sangeetha. I work as a developer at Amazon. A very warm welcome to my talk, The Acid-Base Conundrum. Now, before we unpack the phrases acid and base, I want to quickly touch upon what makes database choices hard. There are two kinds of systems, single node and multi-node system. If all your application's storage and compute requirements can be contained within one computer or one node, that's a single node system. Now, such systems have issues such as single point of failure and the inability to meet growing internet demand. One way to handle growing traffic is by upgrading your system. That is adding more CPU, adding more RAM, etc. This is called vertical scaling, and we know it's impractical to upgrade a system beyond a certain point. So an alternate is to add more nodes to your system. This is called horizontal scaling, and we get a distributed or multi-node system. Now, distributed systems scale really well, but they bring along with them another set of challenges, such as consistency. To ensure every read receives the most recent write or an error. Ensuring availability. That is, every request should receive a non-error response. And partition tolerance. That is, ensuring that the system continues to operate irrespective of any number of messages dropped between the nodes or any network partition between the nodes. Now, the CAP theorem, which was introduced in 2002, beautifully captures all these nuances of distributed systems and dictates that it's impossible for a distributed data store to simultaneously provide more than two out of the following three. That is, the consistency, availability, and partition tolerance. Now, we all know that computers fail all the time, so partition tolerance should be a given. So we are left with choosing between either consistency and availability. Now, is there one answer that fits all scenarios? No. It usually depends on the trade-offs. Taking inspiration from the CAP theorem, one good way to evaluate database choices is to understand the application's CAP requirements. Now, you're all probably familiar with the term ACID. It's used in the context of relational databases. ACID stands for atomicity. That is, all the statements of a transaction happen as a single atomic unit or none at all. Consistency. Any change to the database adheres to the constraints that have been specified on the database fields. Isolation. Two or more transactions can happen concurrently without any interference. And durability. Once committed, the transactions are persisted forever, even in the case of a system failure. Now, it's quite apparent that the ACID constraints are pretty strict, but we are honestly thankful for that sometimes. For example, consider a banking transaction where you and your partner are withdrawing and depositing amount from the same bank account at the same time. Now, during such scenarios, you want the ACID constraints to kick in to ensure consistency and correctness of data. But sometimes availability and scalability take precedence over consistency and correctness. For example, consider your Twitter feed. Now, as much as you would love to be notified the very second that your friend tweeted something, that is not a strict requirement. You're probably okay with a delay of 1 or 2 seconds. So an alternative to ACID called base emerged. Base is basically available in a soft state with eventual consistency. Now, what are soft state and eventual consistency? Let's understand by taking a look at a very high level transaction. Here we have an ACID compliant store that holds the value x is equal to 5. We have two writes x is equal to 10 and 20 approaching the store. Now let's say x is equal to 10 first hits the store. Now the database sets a lock to any further writes to x until the write x is equal to 10 is properly committed. This means the write x is equal to 20 takes marginally longer time to return a success response back to the client. Now let's take an example of a base compliant store. Base stores are usually NoSQL and hence their values are not normalized fully. So the value x is equal to 5 could be replicated across two nodes. Now in a similar way, we have x is equal to 10 and x is equal to 20 approaching the system. A base store does not set locks and thus the values x is equal to 10 and 20 could be written to two different nodes. So for a user who is trying to read the value of x, based on which node they read from determines the value of x they read. But eventually, these two servers communicate between themselves and come to the understanding that x is equal to 20 was the most recent write. So from the soft state where they were holding two different values, they come to an eventually consistent state where they hold the same value. So we seem to have two solutions based on what we prioritize. For consistency, we have the ACID compliant SQL stores. And for availability, we have the base compliant NoSQL stores. Now, as time passed and Web 2.0 happened, large industries such as online retail and financial industries started looking for solutions that brought best of both the worlds together. That is ACID guarantee along with scalability. So the lines started blurring between SQL and NoSQL, and a new era of NewSQL emerged. Some popular examples of NewSQL implementation are Google Spanner, CockroachDB, etc. Now, NewSQL stores are defined as a class of relational database systems that seek to provide the scalability of NoSQL while maintaining the ACID guarantee of traditional database system in online transactional processing. Now, NewSQL is essentially a distributed cluster of shared nothing nodes where each node manages a subset of data. Now, how do they differ from the traditional relational databases? One, consistency. They use distributed consensus protocols such as Raft and Paxos to deliver consistency. Some implementations, such as MemSQL, even allow you to configure or tune the level of availability or consistency that you seek to offer. Second, storage. Traditionally, relational databases read from secondary storage such as disks. But for online transaction processing, as the current data is more important than historical data, the data can be read from main memory in the case of certain implementations. Of course, techniques such as backups and usage of non-volatile RAMs are used for ensuring persistence. Now, that is pretty much what I wanted to cover as part of this talk. As a quick summary, today we started from the CAP theorem and understood ACID and base and how they relate back to SQL and NoSQL stores and the new era of NewSQL. As part of putting together this talk, I referred quite a few good resources and I have linked them in this link. So if you have any further questions, feel free to reach out to me on Twitter. I'm at Sangeetha_KP. Thank you and have a very great Cascadia conference.
Yay! Thank you so much for that talk. That was wonderful.
Thank you, Cassidy.
So we had a few questions. Oh, I think database stuff, there was a great part of the chat that Will said. He said, databases have been the biggest thing I work with often that I understand the least. And so having something that's very well explained like that is very useful to, I think, most of us here in the audience watching your talk. So with all of this new SQL, is it NewSQL, NewSQL? I don't know how to say it, and there's a whole other pronunciation war happening in there. Is that what we should be using? Is that what everyone should be using? Is that the hot new thing?
Right. It's definitely the hot new thing, but it does come with its own caveats as well. It is at the end of the day SQL version only, but it is built for scale. So it ever so slightly prioritizes consistency over availability. And of course, there are several different implementations of NewSQL available. And one of the differences that I mentioned from the traditional SQL is the in-memory storage that they use. So we have to be careful of how much data we are keeping in memory, and does that fit for our application needs?
Cool. Ooh, I can't wait to experiment with it. It sounds very neat.
Yeah.
And so you talked about acid and base and everything. How do you determine if you need acid or base or both in a given
Yeah.
project?
Yeah. Once we have an idea of what our application's end state has to look like, for example, if it's banking application, then we know that we definitely want a very consistent, strong, consistent view of data all the time. But if you are building something like a social media application where we want whenever I hit Twitter, I just want some data. I want something to scroll. It's okay if it's like a delay of 1 or 2 seconds. So at those times, we want to prioritize availability. So those times, base would be a better option. So yeah, it's like looking at the end state of your application and working backwards from that to come to the evaluation of what database to choose.
That makes total sense. And I always feel like the best answer to questions like that is honestly, it depends on what you want.
Yeah, it's true.
Yeah. Well, thank you so much for your talk and for everything. So many people were into this, and I know I was too. I can't wait to go back and look through your slides again, but I really appreciate your being here with us.
Definitely. Thank you so much, Cassidy.
Thanks. All right. And next we have Sean Wang coming up. Let's go.